Hi guys, I've been given this question where we're going to use substitution to integrate this function here. It's asking us to express our answer in exact form, and judging by the function with this pi that we have in it, expressing it in exact form is just going to mean expressing it in terms of pi. So, that's not going to complicate our answer any more than anything else. So, using a substitution. So we're going to use what's called a U-substitution here. Now what I look for when I'm doing a U-substitution is I'm looking for the x with the highest degree. So in this case we've got this x squared here. So I'm going to substitute this part here out for u. So first of all what I'm going to say is let u equal x squared plus 2. Now, what we're also going to write is we're going to automatically, once we've got this u here, I want you to automatically differentiate this. So differentiate u with respect to x and just leave that sitting there. Now what we're going to do is we're going to rearrange this function here. So to start with, what we're going to do is we've got our v equals, because pi is just a constant, we're going to just move it out the front of the integral. So we're going to have is equal to pi times the integral from 0 to 2 of x squared plus 2. Now I put my u what I'm going to be substituting for u, I'll put that at the front, and then that's multiplied by 2x dx. So what I'm going to do now is I'm going to rearrange this. So I'm going to still have my pi out the front. Now I'm going to have my integral. Now what we have to do is, if we're going to substitute for u, we also have to substitute the boundaries of our integration. So we have to say when x equals 0, u is going to equal 2. Because if we sub 0 into this, we'll get 2. And when x is equal to 2, u is going to be equal to 6. So those are going to be the new boundaries of our integration. So we've got from 2 to 6. And what we're going to do is x squared plus 2 is our u. Now 2x dx. Now what I can do here is I can rearrange this differential here. I can move the dx over to the other side, and I can say that du is equal to 2x dx. So that there can substitute in nicely for 2x dx in this function. So we can then write, instead of 2x dx, we're going to write du. So what we're going to do now is we're going to take the integral of this new simplified equation that we've been given. So we're going to have v is equal to pi times, so the integral of this u is going to be u to the power of 2 divided by 2. And we're going to evaluate that between 2 and 6. So that's going to be equal to pi times 6 squared is 36 over 2 minus 2 squared is 4 over 2. And that leaves us with 36 take 4 is 32, divided by 2 is 16. Now because this is an integral is an area, we're looking for the area under this function, so we're going to write this 16 pi units squared. So let's just go through what we've done here. First of all, we found the independent variable with the highest power, and we used the function that was associated in to substitute for a u. We then automatically found the derivative of our u substitute. We then took out the front this constant pi, and rearranged our function. So we had our U-substitute at the front and the rest of our variables at the back. We were able to see then that 2x dx could be obtained using this differential that we got before, and we were able to substitute the 2x dx for du. Once we had all that, and we changed our boundaries of integration based on what u is when x is equal to the original boundaries of integration, we're able then just to evaluate the integral like normal and find the solution that we would have got if we were able to stick this into our calculators. So I hope this video helped. If it did, give it a like, subscribe to my channel. If it didn't help as much as you would like, send us a question and I'll be happy to explain it. Until that time, the only way you're going to get better at these U-substitution questions is by doing lots of them. So you can start to recognize how you're going to be able to substitute the dx values for a du value. So until next time, guys, I'll see you soon.